All right, welcome back. Hope you guys had a great Thanksgiving break. Today is our final new topic for Chapter 5. Okay, so today we're going to finish up talking about exponential growth and decay and half-lives, and then there will be a small assignment again, and that's specified in its learning, and then go ahead and try to work on the chapter review sometime. Those answers will be posted Thursday at 3:20. And then Friday will be our Chapter 5 test. So today we're going to talk about exponential growth and decay at the start. And one word I forgot to put on that technically should be on here is this is specifically for continuous exponential growth and decay. So something like bacteria or stuff like life, births, deaths, that's continuous because it's continually happening. Okay, it's not like at a certain point the number drastically changes, but it's continually happening, either growing or decaying. Okay, so in this case, for continuous growth and decay, we know that y, that is our ending amount. Okay, that's kind of like our answer. That's what we get after t, a certain amount. So ending amount after t, a certain amount of time has passed. Now the a at the front here, that stands for our initial amount. That's how much we start with. And then k, that is the rate at which the growth or decay occurs. Now, if k is positive, then that tells us we're going to be growing. And as I'm guessing you can guess, when it's negative, we are going to be decaying. Now, if you have trouble remembering, just think decay, like at the doctor's office, that's when or the dentist, your teeth are breaking down, less and less teeth. Okay, it's decay means that it's getting smaller. Now, if we look here at example 1, we're going to use that formula. So a certain strain of bacteria grows at a rate of 0.75 per hour. There's 200 bacteria present when the experiment begins. How many will there be after 10 hours? And then it says round to the nearest whole number. Now, sometimes we're going to be dealing in hours, sometimes we're going to be dealing in minutes. The key is that the time has to match our growth rate. Okay, our rate and our time have to be in the same unit of time, which is per hour, and this is hours, so we're good. So if we look here, we're going to have y equal to, we need the initial amount, which it says we have 200 at the start, and then our natural number e, okay, raised to, we need the rate, which is 0.75, and that'll be times time, which is 10 hours. And it says in the end, it says round to the nearest whole number. So if we pull this up, we're going to do, let's see, let me put it over here. So we have 200, then we'll have to do second ln. So second ln gives us e to the 0.75 times 10. We solve that, and as you can see, here's our answer, 361,608 bacteria, if we round that. Now, when we're doing these problems, I want you guys to try to get in the habit of including your label, okay? These are very applicable. These are the types of problems you could see if you go into a career in science or medicine. So let's do our best to add labels, give it meaning. Okay, so it's not just random information, random math problems. Okay, so if we look at example 2 here, here's our function, and C of H stands for caffeine as hours pass, okay, and it's 12e to the negative 0.5 H. Now negative, that tells us it's decaying, meaning as time is passing since we've drank this can of cola, the amount of caffeine in our blood system will be going down. It slowly passes out of the body, okay? And I'm guessing lots of you guys know how that works with like energy drinks or Mountain Dew or coffee. When you drink it, you feel the effects of caffeine. Over time, you feel less and less of those effects because it is decaying. The amount inside your body is decaying. So it can be used to determine the milligram C of caffeine. It says in a person's bloodstream 8 hours after drinking this can of cola. How many milligrams will be present after 8 hours? And then it tells us to round to 3 decimal places. So if we set it up, I'm just going to put y, that's our final amount, equals 12e negative 0.5 times 8, because 8 hours. So once again, it'll be 12e. So I do 12 second ln gives me e. Then I need to make sure I use this negative. So negative 0.5 times 8 hours. And if we round that to 3 decimal places, 0.2197, so that becomes 0.220, and our answer was in milligrams. Now, unfortunately, that still doesn't give us a lot of context because I don't really know what 0.220 milligrams does to a person. But hopefully, as we go, we can kind of add more context to these problems. So if we look here, it says the size P of a certain insect population at time T in days obeys this function. Okay? So P of T, the population after so many days have passed, that's like our Y. And T is in days. So it says determine the number of insects at T equals 0 days. Now, if 0 days have passed, there's a couple ways you can solve this. One, if 0 days have passed, we can look at our initial amount, which our initial amount is 500. So I can just put 500 insects, and that will be my final answer. If you weren't sure how to do that, you also could plug in a 0 here. If a 0 is for T, and we multiply that, we'd get 0 up there. E to the 0 power, like all numbers, e to the 0 gives us 1. Anything raised to the 0 power gives us 1. So then 1 times 500 gives us 500. So if it's the start, you can use the initial amount, but if you forget, just plug 0 in and you'll solve it. Now, what's the population after 10 days? And this tells us to round to the nearest whole number. Okay, so if that's the case, we would have 500 times e to the 0.02, and we'll times that by 10. How many days have passed? So 500 and e to 0.02 times 10. And we will get 610.7. Now it says to round to the nearest whole number. So let's go ahead and round that up to 611. And that is 611 insects. All right. And if we look here, we have a continuous growth rate of 0.02. If we think of that as a percent, that's a continuous growth rate of 2%. Remember, we'd move it over 2. So 2% per day. Now, it says approximate when the insect population will reach 800. So if we're going to do that, we want to know when will my answer be 800? When is y equal to 800? So we can set this up just like before, except now our t is the variable. So in order to solve for that t, I need to start by getting e by itself, which I can do by this basic algebra. Divide by 500. Those zeros will cancel. 8 divided by 5 is 1.6. If you didn't know that, that's fine. Just use a calculator. Okay, so from here, hopefully you guys remember, last week we talked about this. Anytime we have e, you could use a change of base, do log of 1.6 divided by log of e, or we can just use our natural log button. So we can know that the ln of 1.6 will equal that 0.02 times t. So from here, we can just take the ln of 1.6. Now, from here, we still need to divide both sides by that 0.02. And if we do that, so now we'll take our answer and divide it by 0.02. And we will get 23, let's round it to the nearest tenth. I forgot to put that, but 23.5 days. All right. So go ahead now, flip it to the back, and the final thing we're going to talk about in this chapter is our half-lives. So right here, let's read through this science connection. So it says, all radioactive substances have a specific half-life, which is the time required for half of the radioactive substance to decay. In carbon dating, we can use the fact that all living organisms contain two kinds of carbon. Carbon-12, this is a stable carbon, okay, meaning it won't have a decay rate, it won't have a half-life. And then also carbon-14, which is a radioactive carbon with a half-life of 5,600 years. So once again, that means after 5,600 years, however much carbon-14 there was at the start, there's now half as much. Now, while an organism is living, the ratio of carbon-12 to carbon-14 is constant. But when the organism dies, the original amount of carbon-12 present remains unchanged, right, because it was stable, okay, whereas the amount of carbon-14 begins to decrease. This change in the amount of carbon-14 present relative to the amount of carbon-12 present makes it possible to calculate when an organism died. So as long as we know the half-life, which we do, it's 5,600 years, we can compare that. Now, half-lives can also be used in other ways, okay? If you go into science, chemistry, medical field, you'll have to worry about these half-lives. Especially with like medicine, they can be something that can impact someone's life. So, we are not actually going to use our formula. There is a formula to find the specific answer. However, we're going to kind of reason through it because I want us to understand it conceptually. Okay, so it says barium-122 has a half-life of 2 minutes. A fresh sample weighing 80 grams was obtained. After 10 minutes, how much barium-122 will be left? So we can kind of look at these options, and we're going to find which of these it will be. So at the start, we have an amount, and then we also have a time passed. Okay, at the start, when 0, this is in minutes, so 0 minutes have passed, we have 80 grams. Now over time, after 2 minutes, that's one half-life, so half of 80, we would only be left with 40 grams. Okay, after another 2 minutes, so 4 minutes total, another half-life has passed, so half of 40 would be down to 20 grams. Half of 20 after 6 minutes will be down to 10 grams. And then after 8 minutes, we'll be down to 5 grams. And we need to go one more because we have to go to 10 minutes. So after 10 minutes, we'll go down to 2.5 grams. So we can just kind of reason through it. Okay. Now, the reason you don't always do this is because sometimes like 12, 15, 30 half-lives have occurred. So that'd be a lot of work. But in our case, we don't need the actual formula. We can just kind of reason through it and solve it. Okay. So if we look here at example 5, if this is the case, if we had the half-life of ZN71, so once again, that's a name for some sort of zinc product or some sort of zinc substance, okay? And we are not concerned with that 71. That does not affect our answer. Okay, it tells us the half-life is 24 minutes. So if one had 100 grams at the beginning, how many grams would be left after 40 minutes have elapsed? So once again, start with our original amount, which in our case is 100 grams. And then our time at the beginning is always whatever the label is of the half-life. So in our case, minutes, that's what it'll be. And it's always 0, because this is at the start. So 0 minutes. Now, after 24 minutes, that's one half-life, so we'll be down to 50. And then after 48, that's another half-life, so that would be down to 25 grams. All right. On our next one, we're going to have to do a little estimation, because this time, it doesn't always end up nicely. For example, here it says strontium-90 is a radioactive material that has a half-life of 28 years. If 100 milligrams are present now, how much will be present in 25 years? Okay, so 25 years, that's not quite one half-life. So if we think about it, let's draw our picture. If our amount at the beginning, the original amount is 100 milligrams. And our time, now we're going to deal with it in years. Okay, so our time is 0 years. Now, one half-life will occur after 28 years have passed. And that would mean if we started with 100, we'd be down to 50. But in our case, 25 is somewhere in here. Okay, we don't know exactly, but it's somewhere before that first half-life. So if we look, we know it has to be somewhere between 100 and 50. Okay, so it can't be less than 50. So we know it can't be answer choice D, it can't be answer choice B, because those are less than 50. Now, if we think about it, is it going to be really close to 100, or is it going to be really close to 50? And hopefully you guys can reason that 25 years is close to 28. Okay, we've almost gone through a half-life. This is continuous decay. Okay, it's not like it all happens at exactly 28 years, it instantly cuts in half. This has been happening over that time, okay, as it's continuously decaying. So our answer here is somewhere around 53.79 milligrams. And likewise, we got one more problem to do. And once again, we're going to kind of have to estimate. So the amount that we originally start with is 80 ounces. And our time that we initially start with is in years, so 0 years. Now, after 6,537 years, that's the half-life, so we'd be down to 40 ounces. It's at 3,000 years, so that's somewhere in the middle. Okay, not quite to the middle, but somewhere in there. So the half-life will be somewhere in between 80 and 40. So right from the start, I know it cannot be this one. I know it cannot be this one. There's no way for it to grow with a half-life. Okay, and then it can't be less than 40 because that would be over a half-life. So it's 59.26 ounces. Now, if you have more questions about specifics of half-lives, let me know. I'd be happy to talk about it with you, or you can talk with your chemistry teacher. Hope you guys have a great day, and I will see you guys later this week. Bye.